All right, this is a video on solving systems of linear equations with matrices, and we'll start off with an introduction and then do a couple examples. Okay, so as a way of introduction, we need to make sure we're distinguishing between what's a matrix and what's the matrix. The matrix is that movie with Keanu Reeves in it. A matrix is a grid of numbers. Okay, so it's a two-dimensional grid of numbers that have a certain number of rows and a certain number of columns. We typically represent matrices in math with these square brackets. And we refer to a matrix as, we just name it with a capital letter. So this matrix we're looking at is capital A. And we also look at the dimensions of the matrix as well. Okay, so for example, we can think about this matrix as having 3 rows and 4 columns, okay? And a lowercase a, when I'm showing you right here, with a subscript of 2, 3, represents what element in the matrix A is in row 2 and column 3, okay? And that's the 7 right here, okay? I just remember RC Cola from the 1970s or 1980s. RC is RC, rows by columns. Okay, so if you see A with a subscript 2, 3, it means row 2, column 3. So capital letter A refers to the whole matrix. A lowercase a with a subscript refers to a particular element in the matrix. We can write a system of equations as a matrix and use that to help us be a little bit more efficient in solving these systems. Okay, and the way we do that is like so. We want our equations to look like this: ax plus by equal a number. Okay, it looks like my first equation here is set up in that form, but my second equation is not. So I'm going to turn my second equation by adding x to both sides. I'm going to turn that into x plus y equals 6. So now we have a system of 2 equations, both in the correct form. And really, writing a system of equations as a matrix really just means eliminating the x's and y's and also eliminating the equal sign, and we'll have a big matrix that looks like this: 3, 2, 5, 1, 1, 6, 2 rows, 3 columns, and we put a vertical line in here to represent the equal sign. So to try to be super clear here, this 3 refers to this 3. This 2 refers to that 2. And that 5 refers to that 5. Okay? And that vertical bar in between the 2 and the 5 represents the equal sign. So all we did is we wrote our system of equations as a matrix. Matrices, using matrices as a tool for solving systems is a shortcut. We're not really developing any brand new math or anything here. There are many other things you can do with matrices, but here we're just using it as an efficiency tool. And I think it's also, I hope you'll be able to see that it'll be useful as a tool where if we're interested in maybe using a computer to program a solution to a system of equations, we can use matrices to do that. So things we're allowed to do when we solve a system, and then we'll solve one system using a matrix. We can switch any 2 rows. That really just means switching the order of the 2 equations. So that's not changing anything, right? We can multiply any row by a constant. So we can switch any 2 rows, multiply any rows by a constant. That just means we're multiplying the left and the right side of an equation by a constant. That's allowed as well. We can add one row to another. We've done that a lot with the elimination method in solving systems of equations. And then we can combine those 3 steps. Okay, so those are sort of our tools available to us. So let's go ahead and work on solving this system of equations. I think what you'll see is it might end up feeling awkward or tedious or maybe even longer than what you're used to, but I want you to stick with it, and maybe you can also realize the potential of this method as a way of being more efficient down the road. First, what we're going to do is we're going to write the system of equations as a matrix. So 1, 4, -1, and 2, 5, 4, a vertical bar to keep us remembering that there's an equal sign in there, and then a couple square brackets to help us remember that it's a matrix. Okay, so the first thing we're going to do is multiply row 1 by -2, and then we're going to add it to row 2. okay? And then we're going to replace row 2 with the sum, okay? So you might be thinking, how do you know how to do all that? I think you'll see as we go through it, okay? So we are going to keep our row 1, and then our new row 2 will be -2 times row 1 plus the original row 2. And that gives us a 0, -3, and a 6. So maybe you're seeing what that did. What that really got us is this 0 right here. And basically our new row 2 says that -3y is equal to 6. Okay, and it'll be easy to solve for y from there. Okay, so our next step that we're going to do is we're going to multiply row 2 by 1/3, or by -1/3. Okay, and that'll get us what y is equal to. So what we have now, what we'll have after doing that is our row 1 stays the same, and our new row 2 turns into this. This is our goal, to get something that looks like that, a 0 and a 1, meaning that y is equal to a number. Okay, so now we've solved for y. Let's work on solving for x. So to solve for x, we're going to multiply row 2 by -4. And we're going to add it to row 1. And we're going to replace row 1 with the sum. Okay, so let's see what that does. So row 2 won't change. We still have a 0, 1, and a -2. We're multiplying our row 2 by -4, and then adding it to our row 1, and then replacing row 1. And so we will end up with a 0, a 1, 0, and a 7. Okay, so let's go through those steps a little bit more carefully. We multiplied that row by -4, and that gave us a 0, -4, 8. Okay, and then we added these two rows that I'm going to highlight in red. We added those two rows together, and do you see how the -4s eliminate? And that's how we got this row in purple, once we added the two reds together. All right, so let's look at what we have right now. We have our system of equation has been solved. Our system of equations has been solved. Now we could rewrite it as a traditional system of equations if we wanted to. We could just write out our solutions as well. X is equal to 7 and y is equal to -2. So just if we did want to rewrite it as a traditional system of equations now, this would, or convert back from the matrix, 1x plus 0y is 7, and 0x plus 1y is -2. So we have a solution. We could write it as an ordered pair as well. So again, this might seem awkward, harder, tedious, maybe even a more difficult way of solving a system. But I hope you can see some of the potential here where we're trying to streamline the process. And I think a really good benefit of this is developing a method that could be automated perhaps. Okay, so we got through it, and that's a good place to stop.